But can you not see the bottom now? Trying to reduce the amount of like dead space that we lose from the sides of the screen. Okay, so today the main topic is going to be implicit differentiation, but I wanted to follow up on one thing about the chain rule. So you can use the chain rule to derive the quotient rule, and I find that this like helps me remember the quotient rule. So let's do that really quick. So we'll prove the quotient rule using the product rule and the chain rule together. So I'm just going to let f and g be functions. And I'll also let capital F be equal to f of x divided by g of x. So we'll figure out how to take the derivative of this, pretending that we don't already know the quotient rule. So what I'm going to do is first rewrite this as f of x times g of x raised to the power of -1. Okay, so this is also going to use the power rule. Okay, and now I'll take the derivative of this first using the product rule, but then along the way we'll also use the power rule and the chain rule. So then f prime of x. So by the product rule, I'll take the derivative of the first function, so f prime of x, times the second function, which is g of x inverse, plus leaving the first function alone, so just f of x, times the derivative of gx inverse. So maybe for now, I'll just write this as d dx of g of x. Or sorry, I shouldn't say inverse, g of x to the -1. Okay, so off to the side, let's find the derivative of this thing. So what I'll do is by the power rule, multiply this by -1, subtract 1 from the power, and then by chain rule, I also have to multiply by the derivative of whatever was inside that function. So we're thinking of the to the power of -1 as being the outside function, and g of x is an inside function. So this is gonna be -1 times g of x to the -2 times g prime of x. Does that make sense? Other questions? Yeah.
So like on a midterm, if we see like find the derivative of 1 over g of x squared, we should recognize that as g of x to the -2.
Yeah.
When we're like deriving it.
Yeah, so you can yeah, anytime you have 1 over something to a power, that's the same as that thing to minus the power.
So we should see that as like an outside function.
Yeah, you can. Yeah. Yeah, just depending on the situation. Like you had yeah, so say you had a function like 1 over x squared plus 1. You have the option, like you could view this as, oh, interesting, I might have made the screen too big. So you have an option of like, if you had to take the derivative of this thing, you could do quotient rule, or you could view this as x squared plus 1 to the -1. Yeah, and then take the derivative of that. Are there other questions? Okay, so I'm just going to simplify what we have here. So, and actually what we're going to do is factor out g of x to the -2. So if I do that, on this first term, that's going to leave behind f prime of x times g of x, right? Because initially here I only have one factor of g to the minus 1, so I need to leave something here to cancel the fact that I pulled out a minus 2. Plus, made this a little bit too close. F of x times, we pulled out, sorry. Okay, so we have f of x times minus 1 times gx to the minus 2, which we're pulling out over here, times g prime of x. So the minus 1 is going to change this plus to a minus. We get like a blue minus sign, and then we have g prime of x. Okay, and this is the quotient rule. So f prime of x times g of x minus f of x g prime of x all over g of x squared. So, oh, it's really, I made this window way too big. Okay. So, reason why I wanted to show you guys this is because this is just like how I remember which term gets the minus sign. And it's because the denominator function came with a power of -1, and that's where that minus sign came from. So does that make sense? And that also helps me remember that in the end we're dividing by g of x squared. So if you sort of remember, like if you only remember the general shape of the formula, like it's like kind of a product rule thing, but then there's a sign and then also dividing by something squared, like that's like kind of how you could recreate it. Yeah, you have a question?
This upcoming midterm, do we still get a sheet of notes?
Yeah, you will get a sheet of notes. Yeah, so like things that would be helpful to have on the sheet of notes would be like all the derivative formulas. So for example, you should probably just write the quotient rule on your sheet, so you wouldn't be in the situation of forgetting the quotient rule, but and like all the trig derivatives too, I think would be good to include them there. Yeah.
Are we gonna need to simplify now?
No, I don't like, yeah, I don't know, like if you take a derivative of something messy with polynomials, no, you should just leave it. Yeah. Are there other questions? Okay. So let's do implicit differentiation. Okay, so what this is going to allow us to do is to find the equation of tangent lines to curves. So like say in the plane, I have something like, this is like one of the examples that we'll do later today, but some curve like that. It's not the graph of a function, right? Because it fails the vertical line test in a lot of places. But we're still going to develop techniques that will allow us to say, given a specific point on the curve, compute the slope and the equation for the tangent line. So let me just take a moment to say like how you might specify a curve like that, because it's not just the graph of a function. So an equation in the variables x and y gives us a shape. And the shape is going to be exactly the set of points in the plane that satisfy the equation. So this is the set of points x comma y that satisfy the equation. Meaning when I plug in that x value and that y value, I get a true equation. So for example, so I'll start with things that are just the graphs of functions because that's more familiar. But let's say I have the equation y is equal to x plus 1. Okay, so what is all the set of all points x comma y that satisfy this equation? Well, in this case, it's pretty easy to figure it out because if I just plug in an x value, then I get a y value. So if I wanted to draw this, we sort of know that this is just going to be the line going through 0, 1, right, with slope 1. Another like familiar example might be the parabola. So y equals x squared. Get something like this. Another familiar example is the unit circle. So if I take x squared plus y squared is equal to 1. We also know that this defines some kind of shape. And just looks, it's just a circle. And in this case, I can still solve the equation for y, right? I could rearrange this. So maybe I would get y squared is equal to 1 minus x squared. And then I can take the square root and I get y is equal to plus or minus the square root of 1 minus x squared. Okay, so in this case, we can still solve for y. So if I wanted to figure out what this shape looks like, I would just plug in x values. I get 2 possible outputs for y, and then I would just plot them. But there's going to be other cases where you could not solve for y. So for example, the curve that I drew on the board over there, which I'll draw again here. So that is x cubed plus y cubed is equal to 6xy. And it looks like, oh my gosh, that picture I drew on the board. Right, this one, I can't actually solve for y, and so maybe it's less clear how to draw a picture of this, but you know, using a computer, we can get this picture, and the claim is that this set of these points in the plane, if I plug them in, then this equation is a true equation. Okay, does it make sense how we take an equation and that gives a shape? So as like an aside, this is like completely irrelevant to calculus, but my field of math research is called algebraic geometry. And what algebraic geometry does is it looks at shapes that are defined by polynomial equations. You might have like 10 equations and 17 variables, and you can't just plot the shape that you're looking at. And so you have to like figure out how to detect geometric information about the shape just using the equations. So that's what I do. Okay, so and also the book calls this the folium of Descartes. I don't know why. Okay, so these last two pictures that I drew are not graphs of functions. But we can still use the techniques that we've been learning to find the slope of the tangent line at a given point. So that's what we're going to do. So here's sort of an overview of how to find the slope of the tangent line, let's say at a specific point A, B, that's on your curve. So the first thing that we'll do, and this is a little bit confusing, but we'll do a bunch of example problems, is we'll take the derivative d dx of both sides of the equation. So the idea here is that like if I, like let's say I apply d dx to this expression, I know how to take the derivative of things involving x, and then I'm just going to view y as being some kind of secret function that depends on x. So if I take the derivative of this, it's going to just, what I get out of it will involve y's and y primes. So this will involve, this will give an equation with variables that look like x, y, and y prime. And then it turns out that after we do a few examples, I'll explain why, but you will always be able to solve for y prime and the thing that comes out of this. So then you solve the equation for y prime, and then to find the slope at a particular AB, you would just then plug in x equals a and plug in y equals b. Okay, so that's sort of the steps. So let's do an example, and then we'll see if anyone has questions. Okay, so let's look at the circle. So we'll do x squared plus y squared equals 1. And we'll do this, we'll find the slope at the point 0, 1. Okay, so first of all, we already know what this is. Like, we just think about the circle, what should the slope be at this point? 0, yeah. So, right, so that's like the point at the very top of the circle. So the tangent line will just be a horizontal line, which has slope 0. So, this will help us just check that we're on the right path, right? We sort of already know what the answer should be. So let's check that we actually do get that. Okay, so step 1, take the derivative of both sides of the equation. So I'll have d dx of x squared plus y squared is equal to d dx of 1. Okay, what's the derivative of x squared? Yeah, so we get 2x by the power rule. And then now I'm going to take dx of y squared. And I'm thinking that y is like some secret function of x. So by the power rule plus chain rule, I get 2y times y prime. Does that make sense? Yeah. Yeah, so this you could also write as like 2y times dy over dx. Is one of these two things more comfortable than the other one? Which one do you guys like better? The second one? Okay, let's do the second one. So we'll just write it like that. So we'll do dy dx. Okay, are there questions about how I got the derivative of the left side of the equation? Or is it making sense? Yeah. Okay, so the xy squared, you have to do the product rule, and then let me think. I think we have an example that will be more. We'll have one that's along those lines. Yeah, so we'll do something like that. Are there other questions? Okay, so then what is the right hand side? What's the derivative with respect to x of 1? Yeah. Okay, so then step 2, we have to solve for dy dx. So we can just rearrange this equation. So I get 2y. What I'm going to do is always just put any terms that are multiplied by dy dx on the left side and move all the other terms to the right side. So I have 2y dy dx is equal to minus 2x. And then I can just divide by 2y. So I get dy dx is equal to minus 2x divided by 2y, which is minus x over y. Okay, are there questions about this stuff? Okay, so then now if I wanted to find the equation for the tangent line or just the slope, so the tangent line at 0, 1. So then I just plug in 0 and 1. To my equation for dy dx. So I get dy dx is equal to minus 0 over 1, which is just 0. So then if I wanted to write the equation for the line, for me, point slope is just the easiest one to remember. So it's y minus 1 is equal to slope times x minus 0. So we just have y is equal to 1 in the end. You should probably write the point slope formula on your formula sheet. Okay, are there questions about this? Yeah.
So like I get everything kind of what you said. I'm wondering, like, seems like practice this would often be part of you because you don't know in advance what A and B are discussed about being solved for why.
Yeah.
Like, well, I guess, yeah, like purposes of what we're doing, we'll apply this in context. Some and B for.
Yeah, exactly. Yeah, so in the examples that we'll do, we'll be given a point that's on the curve already. Yeah. Yeah, but I think that's a valid question, like how do computers like actually draw these pictures? Not 100% sure actually. I think there's you know, you can do like a naive thing where you just like put in tons and tons of points and see if they're, you know, approximately true, then you add that point to your picture or something. But I'm sure there's like faster techniques. Yeah. Um, okay, so let's do another example. So we'll look at the folium of Descartes. X cubed plus y cubed is equal to 6xy at the point 3 comma 3. So maybe as a sanity check, we can actually just confirm that this is a point on the curve. So here we would get 27, 27, so 2 times 27. And here we get 6 times 9, which is also 2 times 27. So this point is on the curve. Okay, so first we'll just differentiate both sides of the equation. So we get d dx of x cubed plus y cubed is equal to d dx of 6xy. And then what do I get on the left-hand side? Yeah. Yeah. So we do power rule here to get 3x squared and then plus 3y squared, also power rule, but then we also need to chain rule it with dy dx. Okay, good. And then on the right hand side, so I'll pull out the 6 by constant rule, and then I'm product ruling x times y. So derivative of x would be 1 times y plus derivative of y, which is dy dx, times x. Okay. Is this good? Other questions about how to do this? Yeah.
That's supposed to be clear.
Yes. Okay, so now we have to solve the equation for y dx. And earlier I said that it was always possible to do this, and maybe now we can sort of see why. So the reason is because as I'm taking derivatives of things, I'm only ever going to end up with terms that are multiplied by either no copies of dy dx or 1 copy of dy dx. So the entire thing is like linear with respect to, you think about this as like some variable, and so you can solve it. Like you're never, you think about it like as you're taking derivatives, you're never gonna end up with like dy dx squared. Because this usually comes up from doing like a chain rule. Okay, so we'll solve for dy dx. So I'll put all the dy dx terms on the left-hand side and all the other stuff on the right-hand side. So we get 3y squared dy dx minus 6x dy dx. By the way, when I'm doing something like this, a lot of times I like to look at the previous equation and as I'm going, just like put a check mark over the terms that I've already dealt with. So like, I already wrote down this term and I already wrote down this term. So that way at the end, I can kind of look and just make sure that I dealt with everybody. Okay, so then on the other side of the equation, I get 6 times y. That's this one. And then minus 3x squared. And that's that one. And that deals with all the terms. Okay. Other questions? So now I'll just divide by, so I'll factor out dy dx. And then divide by 3y squared minus 6x. So we get dy dx is equal to 6y minus 3x squared divided by 3y squared minus 6x. Okay, so are there questions about how we got to this point? Okay, so then now we look at, so the point that we wanted to look at was so we want to look at the line through 3, 3 that's tangent to the curve. So when so I'll just plug in 3 into this. So I get 6 times 3 minus 3 times 9 divided by, you know what, I'm gonna simplify this first because I have a lot of like extraneous factors of 3. So 2y minus x squared divided by y squared minus 2x. Okay, so now I'll plug into the simplified one. Okay, so 2 times 3 minus 3 squared divided by 3 squared minus 2 times 3. Okay, so what do we get? This is 6 minus 9 divided by 9 minus 6, which will be minus 1. Okay, are we happy with this step? Maybe I'll write dy dx is equal to this. Okay, so then the line, again, just using point slope, I get y minus 3 is equal to minus x minus 3. And that's my, the line tangent to that curve at 3, 3. Okay, are there questions about this example? Okay, I'm gonna give you one more example. Let's do the line tangent to this curve, sine x plus y is equal to y squared cosine x at the point 0, 0. And I'm gonna give you all time to do it yourselves, because I think that there's like, I feel like just watching me do this similar calculations over and over again, might get a little bit dull. So go ahead and give this a go, and then, we'll go through it on the board, and we can check, what you did. So I'll give you like 5 minutes. how are you guys doing? You want more time or ready to discuss? More time? Okay. 2 more minutes. Okay, let's go through this. So, we'll take the derivative of both sides of the equation with respect to x. Can someone say what they got for the left side of this? The reaction sine x plus y. Yeah, so we get cosine. Okay, so we're gonna have to do a chain rule. So cosine is derivative of sine, and then we leave the stuff inside alone. And then we have to take the derivative of x plus y. So for that, we get 1 plus dy dx. Okay, what about the right-hand side of the equation? Yeah. Sorry, I lost you. So minus y, or I think you want the dy dx on the first term, right? Because that's where you were taking the derivative of y.
Oh, right, yeah.
Yeah, otherwise that was good. So, yes. Okay, are there questions about either part of this calculation? Yeah,
So the logic for the first one on the right side is just like power roll and chain roll, is that right?
yeah,
But it's just like, so lower, like you bring down the two and then you take the, on the one.
oh, over here, yeah.
You bring down the two and then you take the thing inside, and that's the dy dx.
Yeah, so maybe it would make more sense. Let me just rearrange these. Right, so this is the derivative of y squared times, or like the other part, yeah. Other questions? Okay, so then, you can rearrange this, so I'll just, skip this part, so, solve for dy dx. And we get dy dx is equal to y squared sine x plus cosine x plus y divided by cosine 2y minus, oh, sorry, I misread my cosine x times 2y minus cosine x plus y. Okay, is this also what you guys got? Hopefully I didn't make any errors when I did my notes. Okay, so then the tangent line at 0, 0. Okay, so what do we get when we plug in 0, 0 to this? So we get the left thing on the numerator is 0 plus cosine of 0 divided by left thing is 0 again minus cosine of 0. What is cosine of 0? Yeah. So this is 1 divided by -1, which is just -1. Okay, good. Are there any questions about this?
Yeah, the purposes of the midterm, I guess should we bring like should we put on our dead sheet something that tells us like what the output of various like term functions are, like in other words, like it's like going to go plus times 0. That like memorize that, or should I have like should bring just a chart that look it up?
Yeah, I think knowing a couple of values of trig things would be helpful. Yeah. Yeah. It has to be handwritten. Okay, if there's no other questions, then I'll see you on Monday. And there are office hours right now, if you do have any other questions about anything.